Last time we did Chebyshev inequality, and before that we did Markov inequality. And we also defined variance from the expectation. Right. So, this is all part of concentration inequalities to understand how far can a random variable go beyond the expectation. So, in particular we learned that even 2 sigma away from the expectation, the probability is very low of that happening. So, of course, it can happen, it is not impossible, but it is a low probability event. Now, once you have variance, let us prove some more interesting properties of that. Right. So, variance was expectation of discrepancy square, right, x minus average, x minus expectation squared. So, let us continue with that formula. What we will show is weak linearity of expectation. So, the lemma we will show is what is weak linearity. So, let xi's be random variables, n of them, and say they are 2-wise independent. So, what is 2-wise? 2-wise just means 2-wise or pairwise. It means that if you take x1 and x2, then they are independent. Okay, this notion of independence that you have already seen. Just that, nothing new. So, say you have 2-wise independent random variables, then the variance of sum is sum of variance. Right, which is an amazing thing, because variance was defined by a quadratic expression in x. Right, there was simply no chance that it will behave nicely under sum, but it does. And the cost, the price of that is, the price you pay is that you have to have pairwise independent. If any of these xi xj's are dependent, then this formula fails. Okay, so I am calling it weak linearity because it is not like expectation. Expectation did not need anything, but variance does. It needs this restriction. But anyways, in many applications this holds anyways, this holds true. So, it is a very useful property. So, proof is quite straightforward. So, you take variance definition, and from that it followed that expectation of x square minus expectation of x whole square, right. So, let us use that. That is not good. It is expectation of sum of xi and that is what I wanted here also, sum of xi. Variance of sum of xi is equal to expectation of this square minus expectation of this thing whole square. right? That is variance of sigma xi, random variable. Now this is expectation of, so when you square, what do you get? All possible products minus, so this will be sigma expectation of xi whole square, right? So you will be multiplying expectation of xi with expectation of xj, and it goes over all the ij's. So ij, when they are equal, this is square. When they are different, then there are two ways, I less than j or the flip. So you get the factor 2 in that case. Okay, and this is how do I work with this now? So I will write this as sigma ij. By linearity of expectation, I get expectation of xi xj minus the product. Right, but what is this? How do I make sense of this? How do I simplify this? So this is where I will use pairwise independence. So here is the claim. I need the claim that expectation of x1, x2, since x1, x2 are independent, by definition what I get is probability of x1 being k1 and x2 being k2 times the value k1, k2 over all k2 real numbers. Right, this is expectation of the product. It's basically the probability times the value. But since they are independent, the probability factors. So what you get is sum x1 k1 times k1 with x2 k2 k2 overall k1 k2, right? That this is by two wise independence, and so that gives you the product. Right, so you have clearly, if you see term by term, then this product gives you all these summands of which appear in expectation definition. So this is then expectation of x1 times expectation of x2. Okay, so what you have shown is that expectation is multiplicative as long as the random variables are independent. So expectation is multiplicative on independent variables. Okay, that is what you have learnt. Now with this learning, you can easily simplify the expression which we had before, right? Because this expectation of xi xj minus expectation of xi times expectation of xj, this is 0 except when I is equal to 0. So you get that variance of sigma xi is equal to expectation of xi square minus expectation of xi whole square. This is the only term which survives in that sum on variance, right? And what is this? This is clearly sigma I variance of xi, right? That was the statement of the lemma, right? Variance of sum is sum of variance. So we have shown this. Other terms have cancelled. That was the multiplicative property of expectation. So that's a very nice property to have. Okay, and let me show you just one example which is already major. It's called weak law of large numbers. So what is this law of large numbers? So it is the following statement. It's a corollary of what we just did. Let's follow quite easily. So define the mean of those pairwise random variables as x bar. Okay, n random variables and sum divided by n, that's the mean, as the average of two wise independent random variables xi's, and each, so recall the setting, right? Setting of this was, okay, no, this is something new. So each identical to a random variable x. So these are just copies actually of the same x, but these experiments were done not completely independently, but just pairwise independently. Okay, so if you look at xi and some other xj, they are independent. And then you are looking at the average random variable x bar. So what you can show for all positive a, the probability that the average is away from the expectation of x, this discrepancy being larger than this a, is given by variance. Okay, so the variance of x decides whether the discrepancy can be more than a. So in fact, if the variance is small, and especially when you keep increasing the number of experiments n, as n tends to infinity, this tends to 0. Okay, so the probability is very, very small that average is different from expectation. That's what you learn. That's what this corollary is saying. So let us prove it. It's quite easy. So just apply Chebyshev's inequality and linearity of variance. Okay, so what would Chebyshev say? So Chebyshev says that you need expectation of x bar and variance of x bar. So let's do that. So expectation of x bar is by linearity, it's actually expectation of xi summed up divided by n, which is just expectation of x, because they are all identical to x, right. And the second thing is variance, which we have just shown, weak linearity of variance. So, variance of x bar is summation of variance of xi divided by n for all I, right, which is, okay, let me do this in a proper way. So, this is variance of summation xi by n. Now, you use the property of variance that variance of a times x is a square times variance, right. So, that is a, in this case 1 by n is the multiplier. So, it comes out and it becomes variance of the sum divided by n square. Now, variance of the sum is sum of variance, which is n times variance of x divided by n square. So, this is nothing but variance of x divided by n, right. So, after this Chebyshev gives you variance of x by n a square. Now, Chebyshev gives variance of x by n a square. So, that is the full proof, right. It is just simple application of what you did till now. And the interpretation is, as I said, if you repeat an experiment again and again many times, look at the average, that is basically expectation with very high probability. So, as n tends to infinity, x bar tends to the expectation with high probability. Okay, the average random variable is just the expectation with high probability, and thus repetition. So, repeating an experiment really takes you close to expectation. Okay, so repetition really takes you to expectation. That is what you have learned from this. So, this is called weak law of large numbers. And let us now move to the third and the strongest concentration bound, which is called Chernoff inequality. Okay, so, you have seen Markov inequality, Chebyshev inequality, and now Chernoff inequality. These are the three important concentration theorems, especially in computer science. Okay, so, the theorem is credited to Chernoff around 1950s. So, let x be a binary random variable, like a coin toss, right, head or tails, 0 or 1, with probability of being 1 is called P. Let x1 to xn be identical to x, and mutually independent. this keyword is very important. It's not pairwise, it's not two-wise, it's mutually independent, which means that any of these xi's, given any of these xi's, even a subset of them, any subset of xi's, some other xj is independent. Okay. So, it is not just between pairs, but it is for any subset. And similarly, any two disjoint subsets, if you partition x1 to xn into two subsets, disjoint subsets, they are independent. So, this is the maximum kind of independence. This is being assumed, and then you will get a powerful conclusion. What is that? So, look at their sum. Sigma xi and a delta, which is a fraction. Then the probability that S is away from its expectation what is the probability that the sum is significantly smaller than the expectation. Okay. By significant I mean 1 minus delta, it is a fraction. So, say the delta is half, then this is half. So, what is the chance that S is half of expectation? Right. So, this is e to the minus expectation of x delta square by 2 and the whole thing raised to n. So, what is so special about this statement is, compare it with the weak law of large numbers. So, in weak law of large numbers you were getting n was coming in the denominator, right, this 1 by n was appearing. So, probability was falling like linearly, linear in n, but here the probability is falling exponential in n. Okay, that is the difference. It is a qualitative difference. So, this is the strongest till now. As the decay in the probability is exponential. In n, which is number of repetitions of x. So, the same experiment if you repeat again and again in an independent fashion, then even this multiplicative, the value of S being multiplicatively smaller than the expectation, this probability is decaying exponentially in n. So, it becomes extremely small. Okay, it can be made very quickly, very small, as small as you want. So, first let us prove it, then we will see more interpretations. So, what is the proof? Idea is reduce it to the only thing you know, which is Markov's. Okay, definition of expectation. So, reduce it to Markov. So, let U be expectation of S, which is expectation of sigma xi, which is actually n times expectation of x. Right, that is what you know. That is what the random variable x is up against, or S is up against. Okay, you want to compare S with n times Ex. Look at the probability. So, that is probability that S is less than 1 minus delta U. So, let us change this to the Markov format, which is you have to flip less than to greater than. How do you do that? You can do that by introducing by multiplying it by minus, but there is a nice trick in the proof which will give you exponential decay, and that is use of exponentiation. So we'll directly we'll write e to the minus ts greater than e to the minus t 1 minus delta u. Okay, for a positive parameter t. And what is E? E is the base of natural log. Okay, so this is around 2.781, I think. So base it's given by power series 1 plus 1 over 1 factorial plus 1 over 2 factorial and so on. So why is this true? These two events are essentially the same, right? They are isomorphic because when s is small, then e raised to minus ts is large, right? S is small means minus ts is larger, and then you get e raised to that also larger. Right? You can check this. So in this way, we have converted less than to greater than, and then you invoke Markov's inequality. So Markov's implies that probability of this random, view e raised to minus ts as a random variable, this being more than e raised to the value, this value is less than the expectation of the random variable divided by this. Okay. Now the expectation of e raised to minus ts is what? So this is expectation of e raised to minus t xi product, right? S is a product. Now the beauty of exponentiation is that product becomes sum becomes product. So S was a sum, and because of exponentiation, this you get actually product of e raised to minus t xi. Now since xi's were completely so mutually independent, you have seen a proof that this will completely factorize. So you will get product outside. Well, now all the xi's are essentially they are the same, right? They are isomorphic to x. So we just have to compute the expectation of this and then raise it to n. So let's do that. So x is binary random variable, so it is 1 with probability p. So you get p times e raised to minus t, and it is 0 with opposite probability, and this thing raised to n. Right. So that's a neat expression. So you know the expectation of e raised to minus ts, and it will help us to simplify it further. So let us write it as 1 minus p like this, and then it is less than equal to, I can write it using e again, like this. Okay, this is because of 1 minus epsilon being at most e raised to minus epsilon. Okay, for a fraction epsilon, you can use this crude upper bound, and so ultimately the expectation is just e raised to minus np times this this parameter 1 minus e raised to minus t. Okay, so let us now go back where we were, which is Markov application, right? So you get that probability of S being less than 1 minus delta u is less than expectation that we just calculated. Okay, let me rewrite this. What is NP? NP is I should have said here that this is equal to NP. So u is actually NP, and let's use that. So it's minus u 1 minus e raised to minus t plus in the denominator you have t 1 minus delta u, okay, which is just e raised to t 1 minus delta plus e raised to minus t minus 1 whole thing raised to u, right. So that is what we have done after this long calculation. We now have a handle, a good handle on probability of smaller than the expectation by a multiple of 1 minus delta. But t is an unknown parameter, so we have to now fix t as a function of delta, so that this right hand side is minimized. Okay, so that is what we will do next.